Hi guys, I'm Chirag Jain, and in this video I'll be teaching you all about terminal velocity. Now you guys might be thinking the movie, right? Well no, I'm talking about terminal velocity in the world of physics. How we understand this in the physical world. That's what I'm going to be teaching you in this video. Now before we actually get to the physics of this part, let's get to what this term actually means. Terminal velocity means the highest attainable velocity. That means the maximum velocity which a body can attain in free fall. You might think that's quite a mouthful, but actually it's nothing but the maximum velocity which a body can attain when it's falling from here to here. That's it. So let's draw a simple free body diagram. Let's take a green apple. They're damn tasty. Now let's see what all forces actually act on the green apple. If this is the surface of the earth, then there's a gravity force which is pulling the apple down. But there's also a resistive force which is provided by the buoyant force of the air. So this is the resistance which is provided by the buoyant force which the air provides. Now that you know what air resistance is, we can actually move on to a few examples and actually get to terminal velocity. Examples are the best way of understanding anything. Now let's assume we have Earth over here. This is the surface of the Earth. And let's assume that a superhero came and took away our atmosphere. So then we'd be left with just buildings but no air. Right? Suppose that's a building and that's you right on the top. And you have this nice big watermelon with you. Now when you drop this, it will attain a certain velocity by the time it reaches the ground, right? Now that there's no air, there's no resistive force for the watermelon, so we can actually calculate the speed of the watermelon, sorry I should say the velocity of the watermelon, with a simple formula. V is equal to U plus AT. V is nothing but the velocity of the watermelon when it's over here. U is the initial velocity. A is the acceleration due to gravity of Earth, which is 10 meter per second square. But actually it's 9.8 meter per second square, but for simplicity, like when we're doing sums, we use 10 meter per second square for simpler math. And let's assume T to be a minute. Let's make the watermelon fall for a minute. Excuse me. If we substitute the values of the given quantities in the equation, we'll get V is equal to U, which is 0, because the velocity of the watermelon over here is 0, plus the acceleration, which is 10, let's put this in brackets, into the time, which is 1 minute. Now don't ever write 1, we always need to take SI units. So it will be 60 seconds, which is equal to a whopping 600 meters per second. That is so enormous that it's nearly as fast as a bullet, which an average bullet has a velocity of 760 meters per second. That bullet is so fast that it hits you before you can even hear it being fired. Now that you know what would happen if we didn't have air, let's see what would happen if we did have air, which is fortunately the case. We have a nice blanket of air around us, a nice atmosphere. Now let's take this as the surface of the Earth. And this time, let's not drop a watermelon, let's drop you. Let's have a plane over here. And we have you. Yep. So the equation for terminal velocity is 2mg by the density of it, the medium, into the surface area, into the coefficient of the drag. Now, I'll give you a few small examples so that you understand how these two are related with terminal velocity. So let's take density. It's really hard to walk in water, right? But it's not so hard to walk in air. That's because density is inversely proportionate to the terminal velocity. Now you might think that inversely proportional, that's so daunting. But actually, inversely proportionate is nothing but the opposite. So if the density goes up, the terminal velocity comes down. That's it. Let's take surface area for example. If you have a body like this and it's moving in air, you'll have more force on it. Like imagine you're on a highway and you've got your hand stuck out like this. You'll have lots of force coming on it like this, right? But if you had your hand like this, you'll have less force coming on it. So that's exactly the same principle for surface area. So the more the surface area, the less the terminal velocity. And the less the surface area, the more the terminal velocity. So again we can say that the terminal velocity is inversely proportionate to the surface area. Now let me just finish this video with a small example of skydiving. Now let's assume you are 80 kilograms. And let's assume, we don't need to assume the density of air, it's 1.2 kilogram per meter cube. Now an average human surface area is about 2 meters square, and G is equal to 2 meter per second square. So now that we know all of these, we can actually substitute them in the formula to find out, and oh, I forgot the coefficient of drag. Let's assume it to be 1, just for the sake of simplicity. Now we can actually find out the terminal velocity of you when you're skydiving. You wouldn't end up like a bullet traveling at 760 meters per second. Rather, your terminal velocity will be 2. Terminal velocity will be 2 into n, which is 80, into g, which is 10, divided by the density, which is 1.2, into surface area, into coefficient of drag, whole under root. Don't miss this root. Now if we calculate that, we would get a value of 2 into 80 into 10 divided by 1.2 divided by 2 and the whole root. You will get 25.82 meters per second, approximately 25. Now this won't be right because the coefficient of drag isn't accurate, but this is how you calculate terminal velocity, and that is what terminal velocity is. As you can see, 25.82 is nowhere near 760 meters per second. So I hope you understood what terminal velocity is, and I hope you enjoyed this video. Thank you all for watching.